In this video, I want to introduce you to a method called variation of parameters. This is a way of finding a particular solution to a non-homogeneous second-order linear differential equation. Okay, we've done the undetermined coefficients, and now we're doing variations of parameters. I'll say right now that I really have a hard time remembering the name variation of parameters and undetermined coefficients. I always get them mixed up. But anyway, this is variation of parameters. So what we're going to do is we're going to start with a homogeneous, non-homogeneous linear differential equation. Not necessarily with constant coefficients. This is the general linear equation. And suppose that I have y1 and y2, which are a fundamental set of solutions for the homogeneous equation. So same left-hand side, but make the g equal to 0. So solve this first. Find two independent solutions. Okay. Now, I've put a star on that one because I want to keep referring back to it. So what I want to do now is I want to just find one solution for that the non-homogeneous equation, right? Find one solution. And what I'm going to do is I'm going to assume that I can find one that looks like this. u1 and u2, I'm going to be looking for these functions, u1 and u2. So that when I multiply u1 times y1 and I multiply u2 times y2 and I add them together, I get another function. And I want to see if I can find u1 and u2 to make this a solution to the non-homogeneous equation. As we saw, I think it was when we were doing reduction of order, that the assumption that I can, just try this, it doesn't limit anything. I mean, if u1 and u2 are constants, then this is very limiting. This is saying, hey, we're taking linear combinations of u1 and of y1 and y2, which of course wouldn't help there, because since y1 and y2 are solutions to the homogeneous equation, if you were multiplying those by constants, you would be getting more solutions to the homogeneous equation. We're looking for something for the non-homogeneous equation. But this doesn't really limit anything, because u1 could be something divided by y1, and the y1s cancel out and you get over the somethings on the top. You can get any function you want this way. Okay. So now, if it's going to be a solution to this differential equation, then that means when I plug it in, the left-hand side should equal g. So I need to find the derivative and the second derivative in order to plug it in. So here we go. This is a product of u1 and y1, and this is a product of u2 and y2, so I have two product rules here. u1 y1 prime plus u1 prime y1, and u2 y2 prime plus u2 prime y2. I should be using like r's and d's, and I could have an r2 d2. Anyway, I'm going to need to take a second derivative, and I've already got four products here now, so there'll be four product rules. So we're going to simplify matters a little bit. I want to insist that u1 prime y1, so this term, plus u2 prime y2, that term, equals 0. They add up to 0. This may seem like, whoa, someone was clever. Someone back in history said, hey, this would be a good thing to do. I don't need every single dang solution to this thing. I just need one, right? I just need one, and then I can add on the homogeneous general solution. I got the general solution to this. So I'm putting more restrictions on than maybe I need, right? But it's going to turn out to help me in the end. So if I make this restriction here that this adds up to 0, then those two terms go away, and I just have that the derivative equals u1 y1 prime plus u2 y2 prime, which is actually pretty cool because it makes it look like u1 and u2 are constants, right? That they just came along for the ride when you took the derivative. No, they didn't really. They just somehow a little magic appeared here, and we got those things to cancel out. Okay, so now I'm going to take the second derivative, which is two product rules. So u1 y1 double prime, u1 prime y1 prime plus u2 y2 double prime plus u2 prime y2. Now plug that all in, second derivative, first derivative, and the function, into the original equation. So here it is. There's the equation again, so I can scroll up a little bit. So there's the second derivative, all of that, plus p of t times the first derivative plus q of t times the function, right? The function was that up there, okay? And that's supposed to equal g of t. We want to see if we can find u1 and u2 to make that work. So let's do a little algebra here. So I'm going to distribute the p of t through there and the q of t through there. Then in the next step, I'm going to gather some terms. So everything that's got a u1 in it. There's a u1 right here. That's a u1 prime. There's a u1 right here. And there's a u1 right there. Those three things I've got over here, and then I factor the u1 out of them. Likewise, the u2. There's a u2 times y2 double prime. There's a u2 times p of t y2 prime. And there's a u2 times q y2. So those are here, the u2 times all that stuff. And then there's a couple of things left over. There's the u1 prime, y1 prime, and there must be a u2 prime, y2 prime right there. So those are right there. Now, something really nice is about to happen. Because the stuff in parentheses here, y1 double prime plus p of t y1 prime plus q of t y1, it's as if you plugged y1 into the left-hand side of this equation. Well, y1 is not a solution to this equation. y1 is a solution to the homogeneous equation. So it doesn't give you g of t, it gives you 0. And all the stuff in that parentheses turns into a 0. Likewise, for y2, it is also a solution to the homogeneous equation. So plugging it into the left-hand side here gives you a 0 as an output, and that goes away. So what this gives us is that if this y, as described here, is a solution to this non-homogeneous equation, then it must be that u1 prime, y1 prime plus u2 prime, y2 prime is equal to g of t. Okay. Now, there's actually two equations that we have because we made the assumption earlier for simplification reasons that we wanted u1 prime y1 plus u2 prime y2 to equal 0. So put those next to each other. And what I have is two equations in two variables, u1 prime and u2 prime. Right? This one has a u1 prime and a u2 prime. This one has a u1 prime and a u2 prime. So these are two actually linear equations in u1 prime and u2 prime. So I can rewrite it as a matrix equation here, where the variables are u1 prime and u2 prime. The coefficient matrix is the y1, y2, y1 prime, y2 prime, which you might recognize that matrix as maybe related to the Wronskian. Yeah. And then, of course, over here is just the stuff that's on the right-hand sides of those equations. Now, we can use Cramer's rule to solve this. If you don't know Cramer's rule, I'd suggest go find a linear algebra book somewhere and look it up. It's a way of writing down the solution of a linear system without actually doing Gaussian elimination or anything like that. It just gives you the solution, what all the variables are. And it involves a bunch of determinants. Okay, the denominator in each of these things is the determinant of the coefficient matrix, which in our case happens to be the Wronskian of y1 and y2. And the numerator, you replace whichever, so I'm solving for the first variable, I'm replacing the first column, whatever that matrix was down there, replacing the first column with those two things, leaving the second column alone. Take this determinant, take that determinant, and you get this, right? Here, this was a 0 times y2g. Right? But it's on the downward side, so it's minus. Down here, when you put the 0 and the g in the second column, then this is y1 times g minus 0, and that's positive on the numerator there. But again, the denominator is the Wronskian. Okay, so we haven't solved for u1 and u2 yet, but we've got u1 prime and u2 prime. So there's only one more thing to do, and that is to integrate both of those. Right? So we can integrate u1 and u2. Integrate those two things to get u1 and u2. And so it looks like that. And the dt's are not supposed to be in the denominator. And there, that's better. So remember, what we were doing was finding u1 and u2 so that yp would be u1 times y1 plus u2 times y2. So once you do these integrals, do this first integral, you got to multiply by y1. Do the second integral, you got to multiply by y2, and then add them together. And that would be the y sub p. And so your general solution to the non-homogeneous equation would be this particular solution that you just found, plus the general solution for the homogeneous equation, which is c1y1 plus c2y2. Okay. Okay, now we need to do some examples and show how this plays out with actual functions, but we will do that in the next video.